flux again, so no current, and then as it comes out, I'm suddenly losing my magnetic flux, and so it's going to try to bolster that up, so it's going to induce a current so that the magnetic field is in the same direction as this external field. That way. All right, so that's just part of it. Is that, you're good on that part?
Yeah.
All right. Now, direction of the force. If I've got a magnetic field that is, or if I have an induced current that's going clockwise, it creates a magnetic field that's going into the board inside and out of the board outside. That brilliant, stunning effect of blue and blue. So I've got a magnetic field as it's here, going in and out. So one way of looking at it is if you look at where's the magnetic field now going to be the strongest? Where is the magnetic field from the induced current in the same direction as this external magnetic field?
On the outside.
Yeah, on the outside. It's weaker here, it's stronger here. The force on a wire with a current running through it is in the direction of the weaker magnetic field. So it's going to be pushed. The force on the wire is going to be that way.
And that is pushing out to the left, or pushing, which line?
It's pushing, as this is going in this way, the force is trying to push it back this way. Because think about alternatively, if it actually were in the direction, that means all you have to do is take a piece of wire, put it near a magnetic field, and it gets sucked in. Think of the damage you can do with something like that. Again, physics leads to weapons. As it's leaving, it says, no, don't leave me. I'm used to you now. But as it's leaving, we have this induced current creating a magnetic field in the same direction, inside and outside. And again, we have a stronger magnetic field here, a weaker one here, and so the force on it at this point is, let's say, so stronger, weaker, yeah, should be that way. So it first says, I don't want you here, and then it says, I don't want you to leave. Magnetic fields have control issues.
Wait, so they're both to the left?
Yeah, did I get some errors wrong?
I don't know, on the answers it said the one of them was the right, one of them was the left.
So I'm going with left on those, so as it's going that way. So if I had a, let's do it this way. Instead of a coil, let me do a square here. So the current is going to be flowing this way. So at this point it's going down. That creates a magnetic field that is out over here and over here. The induced current, so the force would be that way. And over here, if I had a rectangle of coil, the current is flowing this way. It creates a magnetic field out, in. And so the force on the wire would be that way. So I'm still getting left both ways. They said one left, one right?
It says the magnetic field is increasing out of the page, so the induced magnetic field is into the page. Created by an induced clockwise current, the current creates a force to the left.
Okay.
And then it has the magnetic field is decreasing out of the page, so the induced magnetic field is out of the page, created by an induced clockwise current. This creates the force to the right.
Wait, it's at, as it's leaving, it's a clockwise?
It just says the magnetic field is decreasing out of the page.
Oh. No, I had that part right. The magnetic field is decreasing out of the page, so it produces a,
So induced magnetic field created by induced this current creates a force to the right. I think it's for D. I couldn't incorrectly.
changing, magnetic field is decreasing out of the page, right? So the induced magnetic field is out of the page by creating an induced counterclockwise current, okay? The current creates a force to the right. So it's clockwise, so I've got, or counterclockwise, right? And so it's going down over there, so it's going, man, I disagree with them again. Yeah. This is what you get for free. All right, so that's two of them. Okay. Unless there's some subtlety I missed here in the question. Field is uniform inside the rectangle and zero outside. The direction of the induced current. And what is the direction of the magnetic force on the coil at each position shown? So A, C, and E would be zero. Yeah, I disagree with them.
Well, you did say that one wasn't included on the.
Right. There's another mistake in here the student caught. And so I sent it in and said, hey, there's a mistake there. And they corrected it for the next version. So. Eventually it's been corrected in the newer version of this. All right.
So, for 44, is that just, just making sure I'm reading the formula right? Is that saying like number of coils in small equals the number of coils in the primary times the ratio of the voltages?
Sorry, what's your question again?
It's just that's what I'm reading, like.
So we've got a plug-in transformer like that in 2329, which is somewhere.
The formula.
Oh, it's earlier, okay. 9 volts to a video game system, how many turns are there in the secondary coil? The input voltage is 120, the primary coil is 400 turns. All right. So ultimately, okay. So your question again?
Like, so, on the first one, it's secondary equals primary times the ratio.
Okay.
But on the next one, it's primary equals secondary times the ratio. For the
In the,
current.
is it the fact that the ratio is the same?
Yeah, like normally I would assume that the two numbers would flip if you're finding the
The
other one.
difference is that you're looking for power, you're looking for voltage in one and current in the other. So the power is I delta V. This is the energy used per second, and based on conservation of energy, however much energy one loses, the other one gains. So notice that the current and the voltage are inversely proportional to each other, which is why you would get the same ratio. So in the first one, they tell you the information for the first coils and you're finding it for the second. If they had said, if they'd given the current, the input current, and asked what the output current is, then the ratio would have flipped because it's inversely proportional. But because they gave you the secondary information and asked for the primary, so in essence, I1 delta V1 is equal to I2 delta V2. And so they gave you delta, so delta V1, one of these days I'll remember, bring markers ahead of time. Delta V1 is equal to delta V2 times a ratio of I2 to I1.
Well, they gave us both voltages.
Oh, and you had to figure out the number of turns.
Yeah.
Yeah, what I'm getting towards is the fact that the inverse proportionality.
Yeah.
So the current would be proportional to the number of coils, because each coil is going to produce a current. So this is proportional to delta V2 times N2 over N1. And in the second one, I2 is equal to I1 delta V1 over delta V2. Well, delta V1 over delta V2 is, oh no, they gave us 2. That one again. That's 1, 2, 2, 1. So I1 would be, the V2 over V1 is, well, that doesn't get me anywhere. So delta V1 over delta V2 is proportional to N2 over N1. And so we'd have
I1 over I2 proportional to M2 over M1.
I'm getting some backwards here. All right, it's not on the quiz, so I'll address it afterwards. Other questions?
Yeah, for 55.
55, 2 coils are placed close together in a physical lab to demonstrate Faraday's law of induction. Okay, current 5 amps in one is switched off in 1 millisecond, inducing a 9-volt EMF in the other. What is their mutual inductance?
So I get that it's saying that the minus sign is an expression of Lenz's law, but I still don't like understand that. Like why, I don't know why the minus sign goes away in the problem.
The minus sign goes away when you're thinking through the directions. I mean, the whole minus sign is a direction thing.
Alright, it's not asking for direction, it's just
No.
okay. And that M is mutual inductance.
As the magnetic flux changes in the second coil, an induced current is created. That induced current has its own magnetic field, which would be affecting the first one. And that's the concept there.
Well, I'm just saying, is that what that M stands for?
But say it again?
The variable, the M, that stands for mutual inductance instead of L, like it normally is.
Yeah, yeah, probably should remove that problem. Yeah, because I don't think I've ever covered mutual inductance. Inductance. looks like it's just a plug and chug problem. Yeah, let's forget that one too. Other questions? Now let's do this thing. Pardon?
I thought you were second guessing.
Well, I was looking to see if I put one of those problems that I just ignored.